overlap. We pick up in 6372 where we leave off here. So again, in past semesters, I've not done Unit 14 and just covered it in Unit 1. So two things is we'll answer everybody's questions, and we'll cover a lot of material. But there's a lot to it. So if you feel like you don't have a complete understanding of it, I would understand that. You're going to have to work with it, and the project's going to help.
I can't talk.
Uh-oh. I think we got
What? No.
Okay.
What?
All right, we got it settled down. Cool.
All right.
So the other thing is, so don't feel like you have to have it totally in your, under your belt. The other thing is for the project though. And so for the project, it's Unit 13 and 14 homework, so it's got some weight to it, but I'm grading it. How should I say it? I mean, I'm not grading it very tough, super tough. It's got to have all the pieces there, and you got to do your best on it. But it's more of a learning tool than it is a final copy at this point. We want to set you up in 6372, guns blazing, and with a nice running start. So you'll have this experience behind you. So anyway, kind of take it with a grain of salt. If you don't come out of here feeling like you've got it all down, that's totally normal. And again, we'll cover it next semester or in 6372.
Professor, that applies to our exam as well?
As far as Unit 14, I'll have hang on, my phone is, so I guess the question would be, so yes, it does apply to the exam as well, but there will be stuff from Unit 14 on the exam. So of course the question is, what is the stuff that's going to be on Unit 14 from the exam, and what do I mean by just get a good feel of it? So I guess the best thing I can have on that is as we go through this material, maybe as I go through it, I'll kind of point out the things that I think we should definitely have down pat, and the things that will take a little more time. So that's a good point. We'll have a practice exam out probably towards the end of the weekend. We'll have a practice exam out just like we did last time. And what? The test is, well, that's a good question. The test right now is April 29th, which is, I believe, a Saturday. God dang, somebody's got that might be Richard, I'm imagining. Anyway, want to play with our mutes there, but what the heck was I saying? Anyway, April 29th from 11 to 2. So if you can't make that, I'll try to make it, but if you can't make it, we can reschedule a different time. But that's when the final is, and we'll have a practice final out, and we'll have, I imagine, I'll also put a little review out to kind of go over what it is that you should know, because it's a lot of material. So I'll give you a little direction on what you should know and study. And what's Unit 15? So I'll put the practice test out there. I'll put a review out there, and we'll have a normal review for Unit 15. So I guess this won't be the last time we see each other, unless it's totally optional, so you don't have to go to the review. So let's approach it that way. I'll kind of let you know what I think the basics are. But in the meantime, let's use our time wisely and get started with it. Again, fire off any questions as we go. Here is, this is that piece. Where is this piece? All right, so I thought I'd start off here. I've got about 3 PowerPoints, and I'm kind of going to go back and forth between and cruise over to SAS as well. So first thing I wanted to talk about was variance inflation factors, multicollinearity, and let's go ahead and just start there. This is one of the topics that we'll talk about in depth next semester, and other various ways of handling it. And then we'll head into variable selection techniques, and we'll go into some SAS, and then we'll hit some cross-validation, and we'll be set. So this is a good example of how to find the VIFs and what the VIFs can mean and what you can do about them and sometimes what you can't do about them. So this one is one that I like particularly well is the mammal lifespan data. And this is showing, this is the log life. It turned out that a log transformation was needed. This is log life versus log metabolism and log mass. And you can see that the explanatory variables here are log metabolism and log mass. We're trying to see if that's related to log life. Clearly, if we look up here, both of them look like they have strong positive correlation. So again, strong positive correlation. So if I ran two simple linear regressions, I'd expect to see significant slope, and I expect those slopes to be positive. But we see here that metabolism and log mass are super correlated with one another. Have a very strong correlation, a very high sample R, and what could that mean? What that means is that log mass and log metabolism might be confounded with one another. I can't have a log mass. I can't have a big log mass, it looks like, without getting a big log metabolism in our sample. And small log mass looks like small log metabolism. Now, if you fix a log metabolism, notice by fixing, just pick anyone there, I'll just pick one right here. By fixing a value of log metabolism, inside of that, we have some readings of some higher and lower metabolisms. So that's what we're going to do when we actually, that's one of the values of multiple linear regression, is when I do this down here, I run a proc-reg or a proc-GLM, I run a linear model with log life as the response and mass and metabolism, log mass and metabolism as the explanatory variables. VIF is only available in reg. In GLM, it's known as tolerance. And you always want to use, well, anyway, the tolerance is 1 over the VIF, and the VIF is 1 over the tolerance. So whenever you hit proc-GLM, I'll probably have an example of that coming up here. But in proc-reg, you can use VIF, and they're the VIFs. And anything over 4 is sometimes flagged as extreme. Other times, some guidance says to make it more than 10. Certainly, more than 10 is very is kind of universally cause for concern. It's kind of a yellow area between 4 and 10. But these are at 34, so these are very very high VIFs. And what is a VIF? We'll get into that a little bit more. But a variance inflation factor, it's how many times the standard error is, we think the standard error is increased beyond if the parameter estimates were independent. So all that means is that this standard error here, that this standard error is way bigger than what it would be if these parameter estimates were independent. So what the concern of that is, and I'll tell you this, some statisticians say, don't even worry about the VIS. Some statisticians say we got to be really concerned about the VIS. It comes down to what problem you're dealing with, what the interpretation is, what the question of interest is, and kind of where you fall philosophically. So I'll kind of give you both sides. One of them is, this example is great. If these standard errors are inflated, that means that these t-values are smaller than what they should be if they were independent. So here's the big idea is, let's really think about what a big standard error means. And we've talked about this the whole semester, and so we're going to really bring it in here. We know that a t-statistic, and you might write this down on a sheet of paper if you're not just totally familiar with it, a t-statistic is an estimate divided by the standard error. In fact, let's just do this. Oops. Click that. And who's trying to get in? Okay, Max is trying to get in. We should have him in there. Sorry, some people are trying to get in. But I'm going to come out anyway so that hopefully, can you guys, if I share my screen, if somebody would just blurt it out, and it's fine if you can't. The PowerPoint and the chalkboard at the same time here, if I write big enough?
Yeah.
Okay, cool. I'll make sure to write big enough. The two things that we want to remember here, that t equals, in fact, you probably can't see that though, that P equals the estimate divided by the standard error. That's a T statistic. And then also a confidence interval is an estimate plus or minus a multiplier times the standard error. So those are the two big things that should look very, very, very familiar. And that's what we're looking at here. So this p-value is simply the parameter estimate divided by the standard error. You can go ahead and check that if you like, but it's the parameter estimate divided by the standard error. So some people would say in this case that the VIFs don't matter because notice the p-value is still super small. It's still saying it's significant even though the standard error is inflated. Now, because notice what happens here. If the standard error gets bigger, that drives T smaller. If the standard error, if the denominator gets bigger, that drives T smaller. So you would have some concern here if this p-value was greater than 0.05, because you would think that this is bigger than what it would be if they were independent, and thus it's driving it down below the level to have, it's driving your T down closer to 0, which is bringing your p-value down, right? Anytime my T gets closer to 0, anytime my T moves this way, my p-value is, my p-value gets bigger as my T gets closer to 0. And when the p-value gets bigger, it gets bigger than 0.05, and that becomes insignificant. But even though, for this particular example, even though the standard error is thought to be inflated, it's still, this estimate is still big enough that it's still significant. So VIFs here wouldn't matter as much. Now, the other problem is in the confidence interval. If the standard error is inflated, the bigger the standard error gets, the bigger the margin of error gets. And the bigger the margin of error gets, the wider the confidence interval. And so that 95% confidence interval are all plausible values for the estimate. So the thing is, and really trying to ask a question if this doesn't make a lot of sense, we would like to get as close to the truth on this parameter estimate as possible. Because when we use this in the future, if we interpret it, we'd love to interpret it correctly. If we use it to predict, we'd love to use it in the to predict the actual trend correctly. We need this 0.61, this beta hat here, to be as close, to be confident that it's as close to beta as possible. Now, in this confidence interval, if this standard error is inflated, right, that 0.07, that means it's big. And if it's big, that means that the confidence interval around 0.67 is bigger than it would be if they were independent. And so I have less certainty of that parameter estimate is actually 0.616 or that it's anywhere close to that. I have less certainty that I've captured a reasonable interval for that parameter estimate. So those are the concerns with the VIFs. Is that A, your confidence intervals are wide, which means you have less certainty of where the parameter estimate is. If this p-value, if the variance inflation factors are big and the p-value is big, you're thinking that this actually might be a significant variable if they were independent. They might we may be throwing it away, but it might actually be a significant variable in predicting the response. It's just that the standard error is inflated to the point that the p-value is too big. So, but since these reject anyway, even though the standard error is big, if I think it's going to get smaller, that would just make my p-value smaller. If my standard error got smaller, that would just make my p-value smaller, so I'm not as concerned here. The other big piece of this that I know I'm blasting everybody with a fire hose, is notice what happened to the metabolism's parameter estimate. It turned negative. But looking at the relationship between log life, the marginal relationship between log life and log metabolism, it looks positive. How can it have a negative significant coefficient? And that's because multiple linear regression accounts for other variables. So if we just ran metabolism, did I do that? If we just ran metabolism by itself, it would have a positive coefficient, and it would be significant. But since I ran it with log mass, remember the interpretation is holding all other variables constant. Holding log mass constant, that's the only other variable, holding log mass constant, it looks like metabolism actually has a negative effect on the lifespan. And you can think of that as just saying, hey, give me a whole bunch of 100 kilogram animals in the room. Give me a whole bunch of 100 kilogram animals in the room, fixed log mass. Those animals will have different metabolisms, right? They won't all have the same metabolism. And that's saying that those with higher metabolisms, conditional on those 100 kilogram animals, those with higher metabolism should have estimated lower lifespan. But if we don't condition on log mass and we have them go up and down, we had the log mass increase, well, that automatically increases the metabolism, and log mass starts to dominate the explanation of the variance. So that's a very powerful, powerful result there, and it's despite the fact of the variance inflation. The only concern with the variance inflation factor here is that I'm not sure that this is the real relationship between, I'm very certain that it's positive, and I'm very certain that this one's negative, but I'm 616 is close to the actual beta, to the actual parameter. All right, that was a lot of words. Anybody have any questions on that? I'm going to give you a little bit of math here. So this is on the variance inflation factor. So what to take out of this would be the fact that the large variance inflation factors make your confidence intervals wider than they would be if they were independent, make their p-values bigger than they would be if they're independent, and that they're not necessarily something to worry about if your parameter estimates are significant already. And there's sometimes nothing you can do about it. You don't want to drop mass because mass is telling you something about the response. You don't want to drop metabolism because metabolism is significant too. You can't drop them. You're losing information in relationships if you drop them. So sometimes there's nothing you can do about variance inflation factors, and there's nothing that you'd want to do. So here's the variance of the beta J. That's the same as this 0.07161 here, 0.07161. So if I look at the variance of the beta J, that is, what am I talking about? That is a sample. What you're looking at there is a sample, and that is my regression equation. If I took a different sample, then I would get a different, I know I've got the same dots up there, but if I took a different sample, I would get a different regression equation. And if I took a different sample, I'd get another regression equation. If I took a different sample, so you can imagine, even if the red one is the truth, when I take different samples, I'll get different lines because I'm going to have different samples, and the sum of squared residuals will be reduced for different slopes. That's a big concept. Make sure that makes sense. So again, we're saying that's the truth. If that's the truth, then maybe I draw I take a sample, and if I draw a sample, that green line fits the sample. Well, I should have put a different sample on there, but I didn't. If I drew another sample, maybe that green line's the one for that sample. Maybe that line reduces that. This one's showing the variance of the slope because each of those lines have different slope, but they're all coming from the same population. So that one would have a large variance of beta 1/2. Here is the formula for that. Looks complicated. It's really not. This S squared is just the overall. Remember, we're assuming equal standard deviations for all across X for any value of X. So that's really the square root of the MSE, or that is the MSE. That's the MSE from the ANOVA table. That's that S squared. This is just n minus 1, the number of pairs minus 1, number of observations minus 1. And this is the variance of XJ. So did I observe X's that were really low to ones that were really high, or are my X's observed in this little narrow zone right here? This is just the variances of your explanatory variable. Now notice this little piece out here to the end, 1 over 1 minus R squared J. That is the, well, not obviously, this is the BIF. That's what BIF is. Did I put that on here? So this piece right here is the formula for the BIF. And all that is if you regress XJ on all the others. So you'd have a beta naught plus beta 1, XJ plus 1. Somebody can read that, I'm sure. You had XJ beta naught plus beta 1 X j plus 1 plus beta 1 x j plus 2 ... This is a big concept too. Notice that here, y is not a part of this. When you're thinking about the VIFs, the variance inflation factors, y is not a part of it. You're just asking how much is a single explanatory variable linearly related to the rest of the explanatory variables. That's a regression equation. How much of the variance in xj can be explained by the other variables? If that's a high percentage, maybe I don't need xj. Once again, if that's a high percentage, if r squared for this one is big, maybe I don't need it. That's what rj squared is. That is that's the r squared of this regression model. It's just how much can I learn about this explanatory variable with all the other ones in the model? If this is low, then you're like, oh, xj really stands out. I can't do what xj is doing with the rest of these. If r squared is high, then there's a lot of redundancy. And you can see that the closer r squared gets to 1, the smaller the denominator gets, the bigger this factor gets. So the more correlated they are, the more correlation the explanatory variables are with a certain explanatory variable, the smaller this denominator gets, which blows that factor up, which makes the variance of beta j big, meaning that I can't get as good an idea that the estimate that I have is anywhere close to the actual parameter estimate. So that piece right there is something we'll cover in more next semester as well, or you'll get that more in 6372. So the important thing right now is just know variance inflation factors increase the variance of the variance of the the variance inflation factor is the estimated factor of the standard error. How much more, God, I can't even say it. I'm sorry, let me start over. Let me go back to where I can see it. Gosh. All right. So the interpretation of the variance inflation factor is that this standard error is 34 times what it would be if these parameter estimates were independent. So once again, the interpretation of the variance inflation factor is that for this one, that this standard error is 34 times as big as it would be if these were independent. Now we can't just divide this by 34 because these are not independent, and we need this. This is the actual standard error, but we can't just make them independent. One thing you can do is center them. That's another thing we'll go over more next semester. But you can center them, you can standardize them, but then you start losing interpretability.
Professor, how big is big? Yeah, I mean, when watching the videos, you said that, I was watching Dr. McGee, you said that the VIF is big, but okay, it's big, greater than 1, 2, 3, 4. Is it subjective?
4 and 10. 4 is sometimes the some statisticians go with 4, others set it at 10. I'd call it a yellow area between 4 and 10, and anything above 10 is something you definitely should address. But as we mentioned just now, this is well above 10, and there's not much you can do about it. And there's not much you want to do about it because these are very significant variables that are telling you something about each other. But 4 is usually flagged as significant, and 10 is very significant.
Thank you.
Cool. No problem. So this one here, notice the variance of x here, right? The variance of x would be very small because the x's are jammed in here. Notice this next one, the x's are very wide, right? And so that would make that variance of x term would be very wide, and we would have the variance of beta 1. We're looking at a smaller variance of beta 1 because the line doesn't change as much in terms of slope from sample to sample. So there's the VIF, where r squared is the coefficient of determination of a regression of xi on the response of the other predictor variables. So this is exactly what we just talked about. So it's a little visual of what's meant by the variance of beta 1 half. Okay, so when we're looking at that, what do I have here? Yeah, so good. So this is putting CLB. Remember, CLB is the confidence limits of the parameter estimates. And here are our confidence intervals. Notice that 0 is not neither one. So we're pretty darn sure that this one is positive when they're both in the model, that this one should be positive and this one should be negative. but we think that it's somewhere between 0.47 and 0.75, or 95% confident, and this would be much narrower if these were independent. But again, they're not independent, and there's not much we can do to make them independent. So again, some people would argue, don't even worry about the variance inflation factors, and other people feel like there's some important intuition to get out of them. And there are some remedial measures you can take. One of them is getting rid of some of the variables. We'll see an example of that later. But again, you don't want to get rid of one of these because they're both very important, and they're both significant, obviously. So notice that those are negative. That's the only reason I did that. So great, rainfall and wildfires. This is my classic example. So this one is, think about where correlation might enter in here. This is the score. This is basically how many flowers are on this plant, and this is the rainfall. This is the rainfall in January, February, March, September, October, November, December, and this is the total, which is the sum of all these months. So is there any surprise? Check out those variance inflation factors. When I put them all in the model, check out what happens, right? The total is 1,434. That's a little bigger than 4 and 10, obviously, and the rest of them are considerably bigger as well. But why is that? Do we have some multicollinearity going on here? And the answer would, of course, be sure. There's a ton of multicollinearity. Total is a function of 1, 2, 3, 4, 5, 6, 7, these 8 variables. If you increase September, you will increase total. If you increase February, you will increase total. And then you could argue that it's pretty redundant. So what you could do to do one of these, and here, of course, is in ProcReg, you can look at the VIFs, and that's what I've done here. So what you could do is notice this one, I've taken out total. And that's exactly what happens when you have this kind of multicollinearity that is that's variable based. That's just because you have a redundant variable. A lot of times you can take out that redundant variable without losing any significance. Notice real quick the p-values here, right? Look at those huge p-values. No, they're not saying any of those are significant. And then I get rid of them here, and all of a sudden a lot of them are significant now. And that's because those look at those standard errors, right? See these standard errors, 0.7, 0.8, 0.7, 0.7, 0.7, 0.7. And then check out the standard errors here. They're much smaller. So when I divide the parameter estimate by the standard error, it comes up as significant now. And that's simply because it was trying to tell us, hey, you've got some redundancy in the model. Now, we could have eliminated all of these and kept the total and had a more parsimonious model if we didn't care, if our question of interest didn't involve individual months. And that's what I've done here. To notice total becomes significant when you drop the other ones. Which way do you want to go? It depends on your question of interest. Depends on, on how expensive it is to get monthly data. Maybe, maybe it's worth it to you just to grab it at the end and grab some total. But whatever you have it, the very nice variance inflation factors there. And for now, don't worry about variance inflation factors for categorical variables. They do have an interpretation, but we'll cover that more next semester. So what's this?
Professor,
okay, so
what's the partial in the regression analysis? AIC is so it can determine whether how it's going to calculate, getting rid of parameters or not. I would think VIF is the inflation factor, CLI is the interval partial.
Oh yeah, I should. That's a distracting term. This is for partial residuals. And well, I guess we're not going to cover that in Unit 14, but this will generate partial residuals, and partial residuals will help you diagnose outliers when you've accounted for variables. So yeah, I'm glad you're looking really closely at this. For now, let's focus on VIF. We'll hit partial. That I don't actually know if we'll hit partial. When you do partial residuals, that's the term that's just giving you the partial residuals. You can plot those, and all I can say is let me table that for now, just to get on with it.
That's fine.
To get on with the main point. But yeah, I'm glad you're looking at that. The AIC we'll cover a little bit later. That's a CAICS information criterion. That is that's how you can compare two different models. We compared two different models before with the extra sum of squares test. This is a likelihood-based method, the AIC, that allows you to compare two different models. The lower the AIC, the better, and it's just based on the sample and the likelihood of seeing that sample with the given model. And we'll hit that here in just a minute. From here we can interpret parameter estimates. So from here you can just go on with your business, right? This is the non-interaction model, right? These are just adjustments to the intercept. There's no adjustment to the slope. We're saying for these different regions that the relationship between total and rainfall is the same, but their intercepts may be different. And in fact, this is saying that the, actually there should be, oh, well, that's a little bit different. Doggone it. Saying that this uplands, let me go back to the data set here real quick. Yes. I mean, I forgot how I coded that. Hold on here. Oh, no. Couldn't see the actual data. Hang on. Okay, so there's 4. So you just don't see it here. So notice here there are 4 regions: Baja, Colorado, Mojave, and uplands. So there's 4 categorical variables. We have 3 in our model here. And so we can go through and interpret those. And it looks like uplands is significantly different than the reference, which appears to be Baja, because Baja is not in here. So if Baja is the reference, it looks like the only one that's significantly different in terms of intercept is upland. But we can leave that for another day. So types of multicollinearity, there's really 2 types. There's database. That's the kind we just saw with the log mass and the log metabolism. It's in the data, it's in the correlation structure between log mass and log metabolism. There's another kind called structural based where we build it in. And of course, if I include x in my model, and then I include x squared, and then I include x cubed, of course there's going to be multicollinearity between those. Because if I increase x, then I increase x squared, then I increase x cubed. So that's structural based. And again, that's another example of you can center those variables to get their VIFs down to 1, but you might lose some interpretability in that case. But centering does help. So here's a quick example, actually, of an x squared type. So structural-based multicollinearity. We have this tuna example. We didn't harp on this too much, but this is one where we're trying to guess, or we're trying to model the length of a tuna based on its age. We caught all these tunas, and we estimated its age, and obviously calculated its length, and we get this kind of data, and we can fit a line to it, and a line would be significant. Beta 1 would be significant in simple linear regression. But sometimes you just go ahead and fit an x squared or an x cubed term to see if it fits any better. And clearly age and age squared, h2 is age squared, are both significant. And so you've got a model where you've got both x and x squared are significant. And of course, they're going to have high variance inflation factors. And they're both significant already. So you don't really, I'm not so worried about the variance inflation factor here. If I was trying to interpret the confidence interval, I might make note that it's wider, that it's very conservative, that it's very wide. But I'm not worried about this test because I'm pretty sure that age and age squared are both significant. This is one thing you could do though, and that is center the variable. So I'll end up posting these slides, but this is how you center it. So here's age, and you're just going to take age minus 3.628. Notice this is from proc means. So age is 3.628. That's the mean of age. That's the mean of length. That's the mean of age squared. So what you can do is just say S age equals, this is standardized age, S for standardized. Age minus 3.628, that's the mean divided by the standard deviation, and I've standardized it. Once you've standardized it, you don't standardize age squared. You don't take age squared minus mean. That's not the same as once I've centered S age squared is just this value squared. So a quick note on that, and notice what's happened when we when I redo the estimates, when I redo the model, refit the model with the centered one or the standardized ones. Notice that the variance inflation factors have very much calmed down, and of course they're still significant. The only problem is that these guys are less interpretable now, because now they're in terms of standard deviations, not in terms of inches or years in this case, because they're ages. The only downside is the interpretation is now in standardized units rather than the original scale. So the takeaway, multicollinearity is a term that describes the linear correlation between the explanatory variables. It has nothing to do with the response. Multicollinearity can have the effect of inflating the variance of the estimate. Obviously, that's what variance inflation factor stands for. This has the effect of less confidence intervals, of having less confidence in the value that the estimate is wider than the confidence intervals. Our confidence intervals are wider, so we have less confidence in that estimate. It will also inflate the p-values, all things that we've just talked about. The variance inflation factor is a common measure of multicollinearity. You might hear the tolerance. The tolerance is simply equal to 1 over the BIF, and the BIF is equal to 1 over the tolerance. There are two types of collinearity, data-based and structural-based. Methods of dealing with multicollinearity include deleting redundant variables and or designing a better experiment. AKA just designing one where you're not recording variables that are dependent on one another if you don't need to. If the multicollinear is structural, then centering standardizing may help if you don't need to interpret those on a certain scale. Okay, that was great. That was multicollinearity and fairly in depth. Anybody have any questions on that? That came up. If not, we'll head over to variable selection techniques. Okay, so let's go back out and let's just tackle the next thing. This is great. Unit 14, here we go. Where am I? That was Unit 12. Let's get rid of that guy. Or Chapter 12, and here we go, variable selection. So all right, so we had a lot of questions in the quiz on this one. So let's go ahead and check it out. So steps in multiple regression. We're going to plot the data. We're going to develop some tentative models. We're going to develop our questions of interest, account for any confounders, add any relationships that we think might be significant. We're going to fit these models. We're going to get their parameter estimates. We're going to evaluate the residuals to make sure that those parameter estimates are valid, those p-values are valid. We're going to look at constant SD, normality. We're going to look at any influential observations. We'll cover that a little bit more through some examples here. But anything with high leverage and high residual, a residual greater than 2 and leverage near 1, a high leverage is going to have a high Cook's D, and those are ones that you should investigate. It doesn't mean that those are ones that you should delete. So I have a good example here coming up on that where we actually do delete it. But it doesn't mean an outlier doesn't mean we just go look for all the outliers and delete them. As we saw in the last week, right? Last week we deleted 2 extreme observations, but the cost of that was we had to shrink the generalizability of our model. Our X's before that was on the alcohol metabolism study, and our enzymes went from 0 to 5. But we cut out these 2 extreme observations that had a lot of influence, and that shrunk our model. At the end, our model was only valid for enzymes from 0 to 3, not from 0 to 5. So there is a cost that we have to remember when we're deleting those observations. And then we go into validation. So we're going to have a holdout set. We're going to fit our model and then have some data that we didn't use to fit the model to see how well it fits that data. And at any stage, we can go back to the very beginning. So it's an iterative process. Awesome. Answer the question of interest. That's the thing in the end. So when you guys hit your posters for the immersion or any other project or anything at work, you'll do yourself well to just follow these steps in an iterative fashion, just keeping in mind to recheck everything as you go through. So variable selection techniques. We have forward, backward, stepwise, and best subset regression. Let me go ahead and suggest this, because I got some good questions in there. Hari asked a question about why would I ever look at stepwise, why would I ever look at forward or backwards when stepwise is kind of a blend of both. I think Joshua asked a question of related, I'm going to relate all that together, of we're not making any adjustments for type 1 error even though we're conducting all these tests, right? Every one of those rows in a parameter estimate table is a different hypothesis test. And why are we not, they're correlated hypothesis tests, but they're still, you're still inflating the type 1, your probability of making a type 1 error. So those are all problems with these variable selection techniques, is that in the variable selection techniques, especially in stepwise, you're running a bunch of tests. And every time you run those tests, you run the risk of making an error, of rejecting when you shouldn't. And you keep running tests, you're eventually going to reject when you shouldn't, and you might make a bad decision. That's why we always say with any of these selection techniques, the ones that it selects into the model aren't necessarily relevant, and the ones that it leaves out aren't necessarily insignificant or irrelevant. So let me put this last little thing on here before. Every statistician, every data scientist should absolutely know what forward, backward, stepwise selection are, just so you can communicate with legacy code or you can communicate with other people. It's a fundamental piece of it, but they're not used in today's world. They're not used a lot for final model selection, but they can be pretty useful in exploratory data analysis. If you have a ton of variables and you just don't know how to start, you could do a variable selection technique just to see if some of them come up significant, and you just kind of flag them. So you flag the ones that come up significant. Forward selection can be a good use for that, to Hari's question, because nothing is ever taken out of the model. If you're going to use one of these things for just to get a general idea, you just started, maybe in this housing set, you're like, I got all these variables and I have no idea what's significant, then do a forward selection. It's going to go through the variables, pick out the one that's most significant, and then it's going to go through all the variables and pick out the one that's next most significant, so on and so forth. In the meantime, we're going to see this, but in the meantime, if you selected X2 into the model in the first round, that was the most significant, then you selected X5 into the model, well, now there might be some collinearity. X2 might become insignificant. That's where the stepwise regression comes in. But forward is going to keep it in there. So to answer Hari's question there is once it's in, once a variable has been selected into forward selection, it's in there forever. It's in there until you run forward selection again on a different data set. So if you're using this to whittle down some explanatory variables, forward selection is going to give you a list at least of variables that were significant at one time or another. Whereas if you run stepwise regression, it's going to delete those. So I hope I don't have an example here with that because it was just asked in that quiz. But forward selection is going to give you a list of things that were significant at one time or another. Stepwise regression is just going to give you a list of things that were significant at the end, after after it's kind of vetted them. So there's, stepwise is a good regression tool too. But if you're just looking to get an idea of what might be significant and delete some other variables, forward selection can be good for that. Given what we know, well, let's just go through all this, and we'll do these here in a second. There's something else I guess you'll get to next semester called lasso and regularized regression. That includes ridge regression, lasso regression. Those are the ones that are really used most of the time for variable selection and shrinkage. So again, you're going to get into that next semester, but there are other more state-of-the-art methods that have been developed that have kind of take these place, except in exploratory analysis. So forward selection, you just start with no predictors in the model. You go through, you find the one that had the most significance of all the variables. You add that one, and then you go do it again. That's all there is to it. So I'm going to look at 10 variables. I'm going to pick out the one that's most significant. I'm going to put it in the model. Now there's 9 variables left. I'm going to take each of those 9, plug them in with the one that's already in there. I'm going to take the one that's next most significant. And so there's two things. It has to be the most significant of the ones that are left, and it has to fulfill this threshold value. In this case, it has to be, as a p-value, less than 50.15. And you can set this. Backwards elimination is exactly the opposite of that. You put all the variables in the model, and then you take out the one that's least significant. And you keep doing that. So once you take one out, you have to re-estimate all the ones that are in there. And then you take the one that's least significant out again. Then you have to re-estimate all the ones that are in there. Then you take the one significant out. You keep taking them out until you don't have any else that are left that are above the threshold, right? You're not going to look at something that has a p-value of 0.005 and say, oh, that's the biggest p-value, so I'm going to take it out. So you keep taking out the one with the biggest p-value until the biggest p-value is too small. But that's backwards elimination. And then finally, stepwise regression is a mixture of both. So I'm going to kind of show you just a quick little, it's kind of fun. It's like a little game that steps you through stepwise regression. So you don't even really need to know what these are. Just know that there's Y as the response, X1, X2, and X1, 2, 3, and 4 are the explanatory variables. Don't worry about all these complicated chemical names. So there's the data. Of course, we're going to plot it first, and we see some linear relationships here. We see some evidence of multicollinearity. We're just kind of getting an idea of what's going on. So right now, I'm just highlighting stepwise regression, and that's another piece, though, is that stepwise regression doesn't check the residuals between every time. That's another kind of downside of stepwise regression. It's just picking it out based on significant linear correlation, whether that's the best relationship or not. But basically, we start with no predictors in the model. At each step, we're going to add, and then we're going to try to see if there's anything that needs to be pulled out. So really the best way to do this is to see an example. For this example, darn it, I think I'm going to use P of 0.15. It might be 0.05. I forget. But for now, we're going to use 0.15. In fact, I'm just going to skip. You can read this part later. I'm just going to skip it. You've seen the videos. So here we go. So here, we're just going to go step through an example. So this is what it does. In the very beginning, it says, hey, fit a separate simple linear regression for each one. X1, X2, X3, and X4. This is not multiple. This is 4 simple linear regressions. And it says, I don't have any parameters in my model. Let's pick the most significant one. Notice that there's a 0.001 here and a 0.001 here. Those are tied. That's the smallest it'll read. So I go over here to the t-value. I can see that this t is 4.69. I can see that this t-value is negative 4.77. So X4 looks like the most significant one because it's farthest away from 0. So I'm going to select X4. Cool. So notice here at this stage, I've selected X4. My next step is to go pair X4 up with all the other variables that are possible. So now I'm looking at what am I going to add? Am I going to add X1? Am I going to add X2? Or am I going to add X3? So I look at them all with X4 in the model. X4 cannot be eliminated at this stage. It can in the next, on the backward. But I'm doing another. When you start this, there's no variables to delete. I'm not going to add 4 and then delete 4. So I add 4. It's good. Now I look at 1. So I look at 1 here. It's got a very small p-value. That's 10.4. This one, X2's got a very big p-value. This one's got a very small p-value. That's negative 6. I know this one's more extreme. So right now I'm going to. So now my model has X4 and X1. But then I do an elimination step because this is stepwise. So I just added X1. Now I have to go back and look at all the other variables in the model and see if their p-values have changed. Well, this one actually got more significant. There's some multicollinearity there, but it got more significant. So now I'm going to keep X4 and X1. And now I'm going to go see which one I want to add. So I'm going to get X4, X1, and X2. These are the three-way models, X4, X1, and X2, and X4, X1, and X3. Fantastic. Whew. So what happens here? It looks like I'm going to add, try to beat me on that. right? Let's let 0.05, let's let 0.05 be the mark, not 0.15. I think that's a typo. Anyway, both of these would be significant. This one's the most significant, 0.052. So I'm going to pick up the model X4, X1, X2. Cool. So now, I'm sorry, X4, X1, X2, and then I need to do the elimination step. Right? I just picked up X2, so forget about this thing on the bottom here, but I just picked up X2. Now I need to go back and look at X1 and X4 and see if anything became insignificant. X4 became insignificant. So now I'm going to drop them. So in this stage, I said, do I want X2 or X3? I chose X2. Once I know I chose X2, I got to look back at X1 and X4. X4 became insignificant, so I'm going to drop it. So now you see X1, X2. That's my current model. But now I need to go and add, I need to try another addition. I'm going to go look at X1, X2, X3, and X1, X2, X4. So you might say, hey, haven't we already looked at these? We haven't looked at these individual models. We got to keep going until there's nothing left to eliminate. So there's X1, X2, X4. Clearly, I'm not going to add that one. I just deleted X4. So now I look at X1, X2, X3, and I'm not going to add that one either. Right? So now I'm in checkmate. So there's nowhere to add. So X1, X2 is my final model. So that's stepwise. You're going to take a forward step, and then a backward step at each level except for the first one, because you only have one variable at the other. This is just, you probably just get rid of that. Caution about stepwise regression. Remember, whatever's in the, and it's not a magic bullet. It's only based on the data. It's only based on variation, and it can be based on type 1 errors and type 2 errors. So whatever's left in the model doesn't mean it's significant. Whatever's left out of the model doesn't mean it's insignificant. It's just a tool to help you use with other tools to make decisions in trying to form the best model. Many t-tests are conducted in a stepwise regression procedure. The probability is high that we'll include unimportant variables. This is exactly what Joshua was talking about in his quiz question, was we're conducting many t-tests. We have many opportunities to make errors. Drawbacks of stepwise regression. We already talked about that one. It's not guaranteed to be optimal. Stepwise regression is sensitive to models with high multicollinearity. You do want to try to do to get rid of any multicollinearity you can before you do these stepwise procedures. That being said, sometimes you can't. So you don't want to lean, good advice is you don't want to lean on automated variable selection techniques with a heavy weight. You can use them to kind of, as an advisor, you can use them in the very early stages to do some exploratory data analysis, but you don't want to just run it and say, that's my model. For your project, you're asked to do one of each, a stepwise, a backwards elimination, and a stepwise regression. In the project, that's just to get used to you using SAS to fit those, to use that functionality, and to, I forgot exactly what I said in there, and to use the AIC or use cross-validation or some other method to choose between those models. But I'll tell you, in the end, once you finish with our program, with your program, when you finish with this program, you're not going to be using stepwise forward or backward selection in the late stages of a model. I can't imagine a situation you'd be doing that. But you can use it in the very early stages, again, to get to a manageable level of explanatory variables. And the procedure yields a single final model, although in practice there are often several equally good models, right? All models are wrong. We're just trying to find the most useful one. This is a tool to help us early on. And it doesn't take into account any expert. I mean, it'll add, if you're trying to predict sales of ice cream, it'll add shoe size if that's what it should add. It doesn't think it'll add how many books you own. And who knows, maybe that's a useful predictor. But it has no idea of what makes sense in a model and what doesn't. Okay, so to Max's question earlier and to probably everybody else's question, you don't need to know all these formulas. These are just to reference in the future. But we do need to know for your test that AIC, the smaller is better. That's all you need to know about that for now. AIC, the model with the smaller AIC is that's evidence that it's better. It doesn't mean it is better. It just means there is evidence that the data fit that model, that the model fit that data better under the assumptions. The BIC is just the Bayesian information criterion. It's very similar to the AIC. It's thought to work better if you've got a lot of variables that you're really not sure or are significant or not. If you're really just hunting for searching for explanation. In reality, most people actually these days use what's called the SPC, which I don't have on here. That's the Schwartz-Bayesian criterion. The SPC, most people, a lot of simulation studies have shown that that's better, and that's common output. So what you need to know, the AIC, the BIC, the press statistic, that's the smaller the better on that as well. That's just measuring the residual, what's that? That's measuring how much the model's moving when I take out a variable. So if I take out that's one version of the press. You want a small press statistic. Actually, I forgot what press stood for, but you want a small press statistic because let me explain what the press is. So yi is obviously the actual observation, and minus yi hat with this minus I on the end of it means the model fit without the ith observation. So you're not letting the ith observation influence the model at all. So if it's an influential variable, it's not going to move the model at all. So this yi hat is the prediction for the explanatory variables at observation I. It's the prediction of y at I, but without I influencing what the model looks like. And so you prefer to have a small press statistic, meaning that the model fits well to all, and notice this is the sum over all the data. So you want, that's essentially you're looking at a residual between the actual and the observed, but the observed isn't allowed to influence the model. So smaller press, the better. CP statistic, we're going to go over that. We'll go over that one here in just a second. You saw some material. Now it's Mallow CP. You saw some material from the videos from that. That's how you calculate it. You won't need to calculate it on the test. But you should know that some statisticians believe smaller the better. Closest to P, where P is the number of parameters including the intercept, that usually means that your model doesn't have a lot of bias in it, meaning that your model is estimating the truth very well. So I would, if you want my opinion, I would prefer closest to P, but some other practitioners prefer smaller the better. But closest to P is really what's giving you a less biased model. So larger the better, certainly larger the worse. On CP, anything above P is thought to be putting bias in the model. So larger the better. R squared, obviously, we've got to be careful when we use I squared. We know we can overfit. And then we also have the adjusted R squared that we've studied before, which accounts for the number of parameters. Adjusted R squared is pretty good. Again, most people prefer the SPC. I need to update my slides here with the SPC, but those are all ones that are used in practice. So let's check this out. Possible objectives when there are many potential explanatory variables. These are the things that we might want to possibly, these might be our questions of interest. We might always be predicting. We might be fishing for some kind of explanation, and that also kind of falls under prediction. Or we might want to be adjusting for a large set of explanatory variables. Remember, multiple linear regression, by putting more variables in the model, we may not even want to estimate the parameters of those variables. They may be useless to us. We just want to make sure that the one that we are interpreting isn't influenced by those. So again, remember the interpretation is interpreting a parameter estimate is holding all other variables constant. So that could be something like if you're measuring cancer rates and you want to measure if eating red meat is a significant predictor in cancer rates. And then you find out that it is, but you just ran simple linear regression. And then you go and you find out that everybody in your model, everybody in your data set, in your sample, that ate red meat also smoked. Everybody that ate red meat smoked. So you can't tell in the end, is it red meat that's causing the cancer or is it the smoking that's causing the cancer? And if you put one way to handle that, it's not perfect, but one way to handle that is if you put smoking in the model and red meat in the model, then those will account for each other, and you'll see if red, holding all smokers constant. So for all people that are smoking 10 cigarettes a day, if they eat more red meat, does that suggest that they have a higher incidence of cancer? So by putting variables in the model, you can account for possible confounders. So that's another thing we might be looking for here. Okay, great. This is a really cool example. So SAT analysis, the data, we've got this data. It's got SAT averages. We've got takers. This is the percent of the students that take the test in the state. We've got income. That's the median income of families in the state. These are important. The years, average number of years the student received formal education. So the more years, the more education it has in these STEM type of, these core subjects. Public is the percentage of test takers in that area, in that state that attend public schools. Expend is the amount of $100 the state and hundreds of dollars that the state spends on each student, and the rank is the median percentile rank of the students in their secondary school. What the question of interest was they wanted to rank these states, and they wanted to figure out, they essentially wanted to rank these states on who was succeeding the most, who had the best performance on the SAT. But you can imagine that if your percent takers, or here your rank, median percentile rank of students in the secondary school that are taking the test, if the median rank of people that are taking the test is the top 90th percentile, then you've got an advantage over other states that make everybody in the whole state take it. Because some people, like this percent takers, some people make the entire 100% of the state take the SAT. Well, you're going to get the high achievers and the low achievers. But some states only make the top 10% take the SAT. And if that's the case, we need to account for that because that state has an advantage. We're not seeing their low underachievers. So those are some of the ideas that we want to be able to account for in the end. So here's what the data set looks like. We've got every state, we've got their SATs, and we've got their, we've taken the log of takers, and we're plotting the data first. Notice SAT and takers, looks like there's a little curve here with some increasing standard deviation. So we take the log of takers, and, oops, shoot, I didn't replot it, but notice that this is L takers, and this is takers. If you look at L takers, this is, I need to fix that slide. This one looks a lot better when you're looking at L takers. I might have a plot of it later. But this is the log transform of takers. And we look at it, and it looks like we've got some variance inflation. This is B, part of our exploratory analysis. We fit the data, we've plotted the data, we've developed a tentative model that has the things in it that we want to account for, and we see that we've got some variance inflation. Looks like it might be between L takers and rank, which kind of makes sense. The percent takers, the higher the percent, the lower the percent of the takers per state might imply the higher the average or the median rank is of the people that are taking the test, because less people are taking it. So judging from the scatter plot, it looks like takers may need to be transformed. Oh, that's what we did here. So I just kind of went out of order. I got to fix those slides to put them in order. But here's the takers. Here is log takers versus SAT scores. Obviously looks much better. And so here we go. So if we did a forward selection, this may just be something you do in the beginning to see what it has to say. So I do a forward selection. It chooses this model, L takers, years, and rank. Backwards chooses income, years, and rank. And SAT chooses income, years, and rank. How do you choose between those? We can use the adjusted R-squared. That would be one way that we could choose between these. It looks like the forward model has the smallest adjusted R-squared, so you may decide to go with that one. It's not a big advantage there, but that would be one way you could go, and one way you could proceed in the project. So did I choose that one? So, gosh, why did I choose that other one? 88491. For whatever reason, I chose the stepwise model. Judging from the scatter plots, there's no evidence against normality. Why did I choose the stepwise? Well, we'll just go with that. So the adjusted R-squared here is the smallest for the forward one, but maybe that doesn't mean I have to choose that one. So I'm kind of fishing for why I'm choosing this model, but you could very easily just said, hey, I want income in the model. Or I think that there's some collinearity between L takers and rank. And I really would like to not have that collinearity in there, so maybe I'll just take the rank. Exploratory data analysis, looks like I went with the income, years, and rank one. I'm looking at I'm making sure that these, notice the variance inflations are very small. Notice that the residual plots look pretty darn good. Somebody had a question earlier about, how to really read these plots. I'm personally not really worried about anything unless it's in this quadrant here. I'm just going to call it a quadrant, or this quadrant up here. This quadrant has high leverage, very low residual. This has high leverage, very high residual. Those are going to be the ones that have high Cook's D. This is a very conservative mark here. This is 4 over N. This isn't really that much higher than it. It's significantly less than 1. If I was really super concerned right at the moment, I would go look at this observation. I'll probably end up going to look at it a little bit later in the analysis anyhow. But if I was to look at one, that's where I would spend my resources. If I thought this guy here was an error, I wouldn't waste any time looking at it because he has very little influence, meaning that if I deleted him, these parameter estimates aren't going to change very much. So I looked through all those. Looks like constant standard deviation looks all right. Linearity and normality look okay. You definitely, I know I'm kind of breezing through it verbally, you definitely want to write it out on the final, and then your projects. Training, you guys are training to be thorough, well-respected statisticians that put out a great product. You don't want to just say, I checked the assumptions, normality was good, constant standard, or sometimes I just get normality, constant standard deviation, independence, linearity, and that's it. I just get 4 words. You definitely want to write something to this effect, talking about the residual plots. No more than a sentence, but basically a sentence to each one. Outliers and leverage, again, we're kind of zooming in on that. No big deals there. Nothing that's really standing out to me on the Cook's D. This is just going through my analysis. So an expenditure, okay. So let me go back to the question of interest. I should have put the question of interest on there. The question of interest is expenditure. Does it matter? They did want to rank them, but I remember the initial question of interest was, for these schools, does it matter how much we spend on these students? You can imagine that that's a really important question. Does it matter? The more I spend, do I get results? If it is, then I'll spend more. But is there any evidence that the more I spend, the better these mean SAT scores are getting? The first thing that we're doing here is just letting the non-expenditure variables compete to see who is possibly going to be confounded with expenditure. And so we did that, and we came up with income, years, and rank. We checked to make sure that the residuals are okay. We looked at the influential plots. Now we're adding expend back in to see if it's significant after accounting for income, years, and rank. And it looks like it is. It looks like it's not confounded with income, years, and rank, which would be good news for school systems that are trying to get more money. So clearly expenditure each state spends on its students has high significant p-value, and judging from the residual plots, again, we're going to recheck the residual plots. Doesn't look like there's any problems, except for this one. Because once we put expenditure back in, there was something that happened when we put expenditure back in that gave us, look at this plot right here. We're really concerned about that guy because he's driving a lot of these parameter estimates. That is well above 1. It's well into that quadrant. We are concerned with that one. So let's go look at him. So we go look him up. It looks like he's, we could label him, but it looks like it's pretty close to saying that it's observation 29 or 30. So I go look at the data set and check out the expenditures for observation 29, right? 19, 24, 24, that's 50, 21, 30, 20, 25, 27, 26, so on and so forth. So there's something up with Alaska. And the idea here is when they went and looked at it a little bit more, they found out that Alaska, its expenditure, they're not, that expenditure is including the amount spent on heat and air conditioning, and mainly heat. So they're not spending more money per student for instruction and curriculum. They're spending more per student to keep them comfortable with the same comfort that these guys are enjoying at less cost. So that's really an error. That's something that we're using and expend not the way that we want to. We want these expenditures to be on curriculum, not on heat. So we can just eliminate Alaska, but we have to now say that it's only good for the continental United States and Hawaii. This model is no longer can no longer extrapolate, or we'd have to extrapolate to Alaska. So now we see that everything is still significant. That's good news. The parameter estimates have changed probably a little bit. Yeah, notice expenditure was 1.61 here, and now expenditure is 3.38. That could be a very big difference and mean a lot of money to those school districts. Residuals still look really good. My Cook's D's have all settled down now. I don't see anything in the extreme zones, so I'm looking good. After accounting for all other possible confounders, which is why we've got all possible significant confounders, and holding them fixed, we estimate that for each $100 spent on a student in the U.S., excluding Alaska, his or her estimated SAT score increases 3.3851.4 points. That's estimated. And remember, if we kept Alaska in there, that was 1 point something points. So this might be a lot more evidence to talk to the president or the governor to get more money to your school, because it looks like it's helping. Ta-da! That's right. This second analysis is when they wanted to rank them. So that first analysis was to see if expend should be in there, and this analysis is seeing if they want to expend them, to rank them. This is the example in the book, so I'll just leave this analysis for you guys to look at in the book as just some extra material. And we'll move on. This is a good place to ask any questions. I'm surprised we haven't had any here yet. I'm about to hit Mallow CP. You have any questions?
Yeah, Professor, I have a question. So with the selections, forward selection, backward selection, all that, you can manually set the threshold. Is it always good to just set it equal to what your alpha is, their confidence, what you want it to be?
Good question. It depends, again, why you're using variable selection. So the reason why they were set to 0.15 earlier is because obviously if you set them to 0.15 with forward selection, it's easier to get into the model. So if your goal was very early in the model building process and was just to take a whole bunch of explanatory variables and get some idea of which ones might be significant, you may want to, you might have 100 variables and you want to narrow it down to 50. Well, then set it to 0.15 and let it be easier, lower the, don't try to hit a home run with a really significant variable in the beginning. Let them come in because they can change the multicollinearity. So that's when you would set it to 0.15. If you're late, if for whatever reason you're using model selection techniques with variables, with less variables and variables that you think are significant, then yes, set that, make it harder to get into the model and easier to get out of the model by setting that to 0.05 or whatever alpha is.
All right, so you have different thresholds you may want to set whether you're early or late into this model creation, but what is early and what is late model creation? Because it seems like we've just been doing the sort of quote-unquote early stuff. We have these forwards, backwards, and stepwise, and it seems like the later stuff would be what we're letting statistics do. Is that relevant right now?
Well, what we just did, I could see you using it. What we just did here, I could see you using 0.15 or 0.05, just depending on what you really, how strict you want to be. It's just a feeling. I hate to say it's just a feeling, but it's saying, hey, maybe I want to see if expend is significant with all the significant confounders. And what is a significant confounder? Is it something that's significant at the 0.15 level, or is it something that's significant at the 0.05 level? And that's, I don't know how to say anything better than that's just a subjective feel as to what you think is significant. Like this guy here, this income is 0.06, right? And that's, so income is 0.06. At 0.05, it would be left out of the model. With backwards elimination, it would be eliminated. But it's close, you know, and maybe income really makes sense. Income, you know, makes sense to me. You know, the more I spend on these students when the average income in the state is higher, well, even accounting for family incomes, if you spend more on people, on these students, then you still get an estimated higher SAT score. So I would keep income in there, and I may want to set that to 0.15 to keep it, to make it easier to let things get in. Because if you set it to 0.05, you may not even see things come into the model. I know I'm in this gray area, but let's pretend that there's like 20 variables here. If you set it to 0.15, you're not even going to see a bunch of them. Whereas if you set it to 0.05, you're not going to see a bunch of them because they're never going to get into the model. If you set it to 0.15, you'll see them, and then you can make the decision whether you want to keep them or not. So this one, you might have said, oh, income, that makes sense. Let's keep income in the model. Whereas if you would have set this to 0.05, you would have never seen income as a candidate to keep or not.
Okay,
so this is kind of, go ahead.
It seems that the more variables you start out with, the higher you may want to set your thresholds.
The more variables you start
If you
out
have
with.
500 variables, maybe you set 0.15.
Sure.
If you only start with 10, maybe you do like 0.07 or something.
Sure. Right, which equates to being earlier, usually it's correlated with being earlier in your model building, is you've got all these variables, you haven't eliminated any of them yet, so exactly right. Make your threshold a little bit higher to let some get in. You can filter them out based on what you think or based on the p-value. And then, but then once you've whittled them down to a set of a much smaller set that have been vetted, that you think are important, that have decent sized p-values, then you can make your p-value a little stricter to get ones that you're pretty sure are really significant. That would be very unlikely if they were insignificant.
All right, thanks. I think we're getting somewhere.
Cool. All right.
Professor, I have one question. So with respect to variable selection, so if we have to go by some sort of checklist or, some kind of criteria, like, so we are looking for like process of elimination or variables. So we are looking for VIF value, and then the second step is to look for a p-value, like significance of the, the parameter. And then we'll be looking for adjusted R-square. Is that the kind of sequence we're looking for? Like, how do we select the variables or data?
I mean, I guess we could make a flow chart out of it, but I think it would be a circular flow chart. You don't really look at them after you have experience with it, and after you know what it all means. You look at it as a big picture, as a heuristic picture. Because I'm not going to go through and fix all the VIFs first, because if all the p-values are significant, like we saw with the log metabolism and log mass, I don't care if the p-values or if the variance inflation factors are big, because the estimates are significant. However, if I care about interpreting, then I'm really not going to do anything about it. But if I don't care about interpreting, then I'll standardize them, which will drive down the even if they are significant, those should drive down the VIFs, which should make the confidence intervals narrower, so I have a better idea, which will help me with prediction, which will definitely help me with prediction, but it's not going to help me with interpretation. So it very much depends on, all VIFs mean is that your standard errors are inflated. And that means that your confidence intervals are wider and that your p-values are bigger than they should be. And that matters in certain respects more than it matters in others. So So you got to really ask what your question of interest is. Are you interpreting? Are you predicting? Are you doing both? Does it make sense to standardize the variable? Is it interpretable after you standardize the variable? Does it make sense to simply delete it? Is it structural VIFs that we're talking about, or is it data-driven VIFs that we're talking about? And then that goes back to if it's interpretable or not. I mean, that goes back to if you want to interpret or not.
Okay.
So
one additional question, like as per the root, I mean, adjusted R square. So is there a magic number like we're looking for, like less than 0.5, or is it something that least of all these calculations that we're looking for all the different models? So I mean, is there something that number that we're looking for, R squared?
For R squared?
Yes.
Yeah, I got to tell you, like I rarely look at R squared. Adjusted R squared is good to look at, but the only time I'm looking really at R squared is I mean, you can compare two models as like a third or fourth tiebreaker, or if I know that I have a good model and I want to interpret how much variance in the response, if I want to actually interpret R squared. Like R squared is very interpretable, so once I have a good model, I can interpret it and I can use it for that. And if I need like a third or fourth round tiebreaker, I could look at that. But most of the time when you're comparing two models, you're not going to look at R squared. You're going to look at the adjusted R squared or something like the SBC or a cross-validation statistic.
Okay, thank you.
So right, and if we're talking about the AIC and we're talking about the adjusted R squared, no, there is no magic number. It's just you're measuring them relative to other models. The adjusted R squared doesn't mean much with just a model. It doesn't mean anything with just one model. It means a lot when you're comparing two models or three or four models.
Okay, got it. Thank you.
Cool. So, great. One that I really like and that I think is underused is Mallow CP. And Mallow CP looks at all subsets. And it does it, it's computationally intensive because it fits a whole bunch of models. And then the idea is mathematically that the closer this CP statistic is to the number of parameters, the better the model you have. And then we can look at the output here. So you just do selection equals CP. It fits all of these models. And it gives you the CP statistic. Now, what is it? I forget. I believe this number in model, that's the number of parameters in the model. This is not well done. SAS does some things great and some things not well done. This is the number of parameters in the model. You need to add one to this to get to what you're comparing CP to, because it's not including the intercept. So really you're comparing this 4 to 5, and you're comparing this 5 to 6, and this 5 to 6, and this 7 to 7. And right there would be a model that I would think would be pretty good, because the CP is 7 and the model 7, and it's got all these variables in it. Now, what you're going to run into is you're going to have some VIF problems between L takers and rank. But then again, that goes down to maybe you don't care at all about L takers and rank. You just want to interpret expend. And so in this case, you would say, well, let's just put them all in the model. This looks like a pretty good model. Let's put it all in the model and see if expend is still significant or not. And then I've counted for everything. Another statistician might say, hey, I prefer smaller models. I like Occam's razor and the principle of parsimony. Look at the R squared here, and I know it's got the R squared. I prefer to see the adjusted R squared, but it doesn't look like there's a lot going on. We know that the adjusted R squared is a function of R squared, and the sample size isn't changing, and the number of parameters in the model. So that being said, knowing what you know about adjusted R squared, which is a perfect example of why you should be familiar with the formulas and not just look at the results, is because now we can quickly say, hey, there's not a big difference between this R squared, 0.9128, and this R squared, 0.9107. But there is a significant difference in this one has 2 less parameters. So for 2 less parameters, I only lost about 21 thousandths of an R squared. And so if that's the case, maybe you just take L takers years expend and rank, which you're still going to have this VIF problem, but again, maybe you don't care because you're only interested in looking at expend. it would be interesting. I'd like to see the model. I'd like to see what VIF, the expends VIF is. I'm pretty sure LTakers and ranks VIF will be high, but I wonder what expends VIF is, which just means how much is expend related to these other three variables in the model. But anyhow, it's just based subjectively on these top four models here. This model is terrible, right? Once we hit to this model, that CP is well above 4, and the rest of them, are just, you can kind of discount them. But these top four here look pretty close. The CP plot tells you the same thing. That line there is the line CP equals P. So again, that's CP equals P. And we can see that these are all below. That's the one that's at 7.7. So that's the one that I particularly liked. But these other two are good candidates. Even these guys could be okay if you like them, but certainly these guys are ones that you wouldn't want to consider. So what did I do here? I don't know what I fit that to. So we have residual influential points. So I picked one of these models. I guess I need to write on there which one I picked.
If you go to the next slide, you can see the R value, and then we'll compare that back.
Oh, good. 0.9107. So yeah, I think actually, now that I think about it, I think SAS just picks this top one at the end of this. You're asking it to make a selection based on CP, and I think it just picks this top one. But you can override that and just go fit one of these on your own. But yeah, so 0.9107, it just grabbed this one. I looked at the, seemed like a pretty parsimonious model. I looked at the residuals. Residuals look pretty darn good. I don't see anything that's really causing influence. So one possible subset of variables that explain the variation in SAT score was the CP. That was a good call there, Joshua. Nice. And there it is, our LTakers rank years and expenditure variables. So the rest of this is, well, so this is the one, this is two garbage slides. I need to get rid of those. But this is how you use ProcGLM select with variable selection techniques. So it's the same exact way as ProcReg, and you're going to be using ProcGLM select a ton, starting very early in next semester. So rather than use ProcReg, you might at least try ProcGLM select to do this. I think that's what Dr. McGee used in a lot of the videos anyhow. But there's a lot of other selection techniques that we're going to use that essentially, except for exploratory data analysis, will make these obsolete. And when you run ProcGLM select, that's another big piece. You get the AIC, you get the AICC, you get the SBC. SBC is primarily the one that I would use of the criterion. You have your adjusted R squared. Once you're sure you have a good model, you can interpret the R squared, but that's that. I don't know which one that one was for.
Professor, I have one question.
Yes.
Yes. So the question, I think I sent an email, or I think in the quiz. So once we select the variables for our model, and then so are we going to run like forward, backward, and stepwise for the same model, or are we expecting? I mean, I don't know. Is it like generally there's expectation, or we can select different variables for like forward, backward, and stepwise? That's kind of a analysis 2 question. I mean, in the previous slide, you showed like, okay, you have like, you selected like specific like variables, and then basically the example shows forward, backward, stepwise. Is that the way we think generally we do, or we can actually have a different model for each one of them when we're actually looking for some kind of a better model?
So at the end of each of these, it will suggest a model for you. They may be the same model, but at the end of each of these, it will give you a model. This is like this. This is probably the output of one of these models. of one of these selection techniques. I'm sorry. Can you just tell me that one more time?
Okay.
I'll try to
Okay.
get you a good
So,
answer.
I mean, in this slide, you see those model has, okay, SAT equals like takers, income, years, public, and rank. You got 5 variables, right?
Right.
And so in all the 3 models, when you're running like forward, backward, stepwise, you have the same variables, right? So we get same 5 variables, right, for all these 3 selections. So is it the way that we generally expected to do when we compare the models, or we can have like different set of variables when we run? Like I'm going back to our analysis question 2. Like we have 80 variables, right? And so we're going to create a model, like subset of those model, like variables we're going to use for our model. So are we going to run the same, like we pick set of variables and then run forward, backward, and stepwise for all those, the same set of variables?
So I think I got it now. Yeah, and that's a really good question. And it comes up with a strategy. What is the strategy for taking a large number of potential explanatory variables and turning them into a smaller, hopefully more significant subset? And that is, so one way that you can do it, and it's all based on time. It's all based on time too. So one way you can do it is to basically like have a tournament. So try to get rid of the multicollinearity. So if you have 80 variables, make 8 subsets of 10. Try to break those up into things that make sense and run variable selection techniques on each one and see which ones come out to be significant. You can make a smaller subset based on that. If you have the time, you can run that tournament with forward, backward, and stepwise. You'd be really, you'd have more confidence in those selections if forward, backward, and stepwise all selected basically the same parameters out of all 8 of those subsets of 10. So that's one way you can do it. One way that's not as good to do it, in my opinion, is to put all 80 together. So say SAT equals 80 variables, and then say selection equals forward, because you're potentially going to have a bunch of those are going to be confounded with the other ones. So I think it's better to to break them into, say, 8 sets of 10, and then see which ones come to be significant out of those. Could you be getting rid of significant variables? Certainly. But all models are wrong, and yours is inevitably going to be wrong. It's just there's a lot of levels of wrong, and there's a lot of levels of more right. And so, so along the way, you're probably going to eliminate a significant variable. But the idea is that on the whole, you're including as many as you possibly can, given the very short time period that you have to do this project.
Okay, perfect. Thank you. And one last question I have on the CV press. I know, like, did we cover, like, I think in the output we were looking for, like, Kaggle score and the CV press. And are we going to look at that today, or did we already look into it? Did I miss something?
So let me look at this project.
The cross-validation value something.
Obviously, we've run out of time, and I've got to actually have to run today, and I know everybody else does usually. So thanks for sticking in there. Let me bring this up and see. I've got 3 projects running right now. I forget what each one is. So let me go to 6371 to units, project, this guy, project description. Okay. So build the most predictive model for sales prices.
You can go down the table, you look at the table, like you go to the next page. Yeah, here. You have this CV press, right?
Yeah.
That value.
So it was a little ambitious for me to get to that. So I guess what we're going to do is we don't have time to actually cover in live session. I can do it in office hours, but let me read in here what I said about cross-validation. So we don't have time to really cover cross-validation. You're going to get a heavy dose of it in the beginning of next semester. I've got some slides on it here. The CV press is this cross-validation press. And I'll cover that in office hours, but basically, if you provide a CV press and you do the research on that, I think I'll just make that extra credit. You can still get a Kaggle score without doing the CV press. So I don't see anything here that'll generate adjusted R-squared, Kaggle score, your paper, please include your tables and post public scout, Kaggle score, quick note on Kaggle completion. Okay, it's just saying don't worry about getting too high a score. So let me see here, cross. So I don't see anything in there. So if you can come up with the CV press, don't worry about if you do the CV press, I'll write this in here. I'll give you an extra 3 points if you come up with if you can figure out the CV press. And that shouldn't be too hard to come up with, but it's totally optional. So note for extra 3 points for calculating and interpreting 1 or 2 sentences, the CV press. Cool. So I'll update it with that. But don't think you're missing something because that's central to where you're going to start in Unit 1.
Okay.
Yeah, you're good. So,
Professor, did you get any answer in terms of classes for the summer for Stat 2?
That's a good question. I looked into it and I have no information.
See you in the fall then.
Well, I've got emails out, so I guess everybody's just busy right this second. I think they would probably respond to your emails pretty quick. Has anybody tried to email?
Oh yeah,
you?
absolutely. They're looking to.
I thought they added 3 new sections.
Oh,
I didn't get a response.
three new sections. They got 6 sections now?
I think so. I thought they did.
Oh,
I
wow.
thought those were all
because I
adjunct
looked out
professors,
there.
though.
What's
They're all
that?
adjunct professors. They're all adjunct professors. Guess what? I'll wait for the fall.
Well, I'll check those out. I didn't know they added them. They might be really good ones. I'll give you my opinion on it. But yeah, that'll be something I'll have to look at. But yeah, I don't have any new information. But yeah, that's good news that they're available, and I'll look to see who's teaching them. But shoot, sorry I didn't get the CV press. And actually, what's going to have to happen here? Office hours this week are when did I say the project's due?
25th.
Oh, that's next week. Yeah. Okay.
It's like Wednesday.
When's the final?
29th.
25th. The final's the 29th. 29th, 11 to 2. The 25th is what day? Did you say it was a Wednesday?
Tuesday. 25th is Tuesday.
Okay. So cool. So I'll have those office hours on Sunday. I'll be in San Diego, so we'll just don't want to surprise anybody when you get a weird background. It won't be the chalkboard, but if I see you there, if not, I'll see you next Thursday, Unit 15. It's optional, totally optional, and stay tuned. Over the weekend, you should find a practice final at some point. So finish up that project, check out the practice final. We'll review on the 15th, and we'll let it rock on the April 29th. I will prepare you well for the final though. So it should be 3 hours, just like it was before, and we'll be ready to go. Cool. Hey, so I'll see you next week at Unit 15, but this is really the end of the new material. I hate that I'm in a rush, but it's been awesome. You guys are great. You're headed for, everybody has grown a ton from the start to the finish. I've met some of you guys in the immersion. I'm really happy with where we've gone as a class. Really go back, look at those homeworks, look at this review that I'm going to give you for the final, look at the practice review, and and I think everybody should, you know, I don't know what your goal is grade-wise, but I think I'm pretty happy with where everybody's been. So you should feel good about where you are. We'll leave the grade aside, but I don't see anybody doing terribly, and I see a lot of really good, a lot